Hello students, in this video we are going to learn about data path design using HDL. In our previous video we saw about system based design using HDL. There we saw an example of your hardware description language and we are using Verilog as the language. And we saw an example of ALU. Here we will be learning about data path design. I hope you remember the unit data path design. There we have seen certain modules, means an arithmetic operation or various operation will be carried inside your data path components. So first thing, when you are doing the data path design, you must make sure that you know what are the data path modules. So I hope that in unit 3 we have already covered about adders and multipliers, shifters. So all these things will come under data path design. So how am I going to design all those data path components by using HDL? So right now in this video we will be learning about few of the data path modules named adders as well as a multiplier. I'm going to show us an example of HDL and the coding is done by using Verilog. So now see here, whenever you are starting with your data path design, the thing that or the module that will come into picture is nothing but your addition. So thing is, addition will be performed by using adder. I am just explaining you about a simple half adder, means I will be having two inputs. So what is a half adder? Half adder is nothing but it will be going to perform an addition operation by using two inputs, and there will be a sum and carry are the outputs. And I said in previous video that this RTL level or your HDL language will be having three different models for coding. So what are they? Structural modeling, data flow modeling and behavioral modeling. In our previous video we saw the coding by using behavioral modeling, means the behavior of my circuit was taken into account and with the help of my behavior I have written a code. Whereas now we will be covering about the structure wise, data wise as well as the behavioral. So all three different modeling of half adder circuit will be covered in this video, added with some full adder program as well as a multiplier. So we'll start with the module. So half adder, which is two inputs are the A and B, and sum and carry are the outputs. The diagram that has been shown down is nothing but the half adder picture. So what are the gates that we do have in this half adder? We have an XOR gate as well as an AND gate. So XOR gate is nothing but it is going to produce a sum output and AND gate is going to produce the carry output. Now I am going to show, I told that there will be a module and the module name is half adder, and inside the bracket we will be specifying the input and output variables. So what are the inputs and output? As I said, it is A and B, and sum is output and same goes with carry also. So I am specifying my inputs, which is input is A, again input is B. I can write input A comma B also, and output sum, again output carry. Okay, so now I'm doing the XOR operation. See, I'm not saying the syntax, place the semicolon over here and there. I'm not explaining you all those things. I'm just explaining you what actually is the structural level modeling of your half adder. So XOR of, see the structure, I'm having an XOR as well as an AND gate. So while you are doing the structural modeling, you must know the structure of the particular circuit. Okay, so what are the gates that I do have? An XOR gate. So XOR of U1. So I'm going to give the name for my gate as U1. Okay, so XOR of what is the output? Which is output is sum. So first you have to specify the output and then you have to specify your inputs. So XOR out gate is the gate, and the gate name I am giving as U1, and sum is inside the bracket I have mentioned sum comma A comma B. So whenever your program sees this or the coding, when you are simulating this particular program by using the Xilinx, while simulating I will be having A and B will be passed into, or A and B we will be giving us the input, and that A and B is going to perform an operation. What operation? XOR operation will be done, and the output will be stored in sum. Okay, and the next C for AND gate, AND, which is a second gate, which is U2. I'm just calling the name, it can be any name. So AND of, what is the AND output? Is carry, and what are the inputs? A comma B. So simple. This is a structural level modeling of your half adder. So know the structure, write the name of the gate, give a name for the gate, and open the bracket and mention the output first, comma, and then mention the inputs. Okay, that has completed the structural level modeling of half adder. We shall move into the second model, which is called as data flow modeling. So in data flow modeling, we will be using assign statement. As a shortcut, I'm explaining you, whenever you see an assign statements inside your program, you can say that it is your data flow modeling. Means I'm going to assign some data after that has been processed into another variable. Okay, now see the module half adder, the same thing. You can write the same thing, input A comma B, output the sum and carry. The module has been completed, and in that what I'm going to write, what are the things? See, I can make it as input A comma input B, output sum, output carry, everything inside the, while I am declaring the variables itself, I can declare my what are the inputs or what are the output. So these are the two different ways I can mention the module or my ports. And then we are going to perform an assign, which is data flow modeling. Means what is sum? Sum is nothing but an XOR operation of A and B. So A XOR B. So only if you know the operators properly, we can go for the data flow modeling. Okay. So what is this XOR? A XOR B, which is stored as a sum, which is yes. That I am assigning it. Again, what is carry? Carry is AND operation. So C is equal to A and B. And then we are going to complete your program as end module. So if it is a structure, you can write the mention the gate name. If not, if you know what the gate is actually, and if you know the structure or else your operators, you can go for this type of data flow modeling. And you see that this is nothing but a half adder by using behavioral modeling. Means previously we have seen always set also. Always set, whenever your x or your y is going to change, I will be beginning my program, and if my x is equal to 0 and my y is equal to 0, okay, it is a logical AND. Okay, it is not bitwise AND, it is logical AND. If you have a doubt, you can go for the previous video that I have mentioned you what actually is a bitwise or what actually is a logical operators. So if my a is x is 0 and y is 0, I can begin my program. My sum will be 0 and carry will be 0. And then else if, what is the else if condition? If my x is equal to 1 and y is equal to 1, I can say my sum is equal to 0 and carry is equal to 1. Else, again I will be beginning. It will be by default, the sum will be 1 and carry will be 0. See, this has been drawn with the help of a truth table. You just write the truth table of a half adder and make sure x or y are the inputs and sum and carry are your outputs. Just you mention 0 and 0. Sum is 0, carry is 0. And again 1 and 1, sum is 0, carry is 1. For other cases, definitely your sum will be 1 and the carry will be 0. That is what has been mentioned. So based on the behavior of your program or behavior of a circuit, I have mentioned and I have used that behavior to make a half adder program. So these are the three different modeling for a particular half adder structure. And now see, you may get a question like design or write a program for a 4-bit triple carry adder by using full adder. This is the most important question that you will be getting it again and again. See, design a 4-bit triple carry adder using full adder. Okay, using Verilog or write a program, they may ask. So see, the diagram that I have drawn above is nothing but a ripple carry adder. So there are four full adders were there. Okay, so 4 full adders, which is x0 and y0 are your inputs, and I will be getting s0 and sum not carry not as the output. The same way x1 y1, x2 y2, x3 y3, which is 4-bit. So I'm having this ripple carry adder has been already covered in our previous video, make sure. And now go for a structure. What is the structure that I have drawn? This structure is nothing but it is a structure of a full adder. So full adder is going to add three inputs, thereby x, y and carry in or my input sum and carry out is the output. So inside all my full adders, I will be having this structure. So now see, what is this? I have written a module for a full adder first. Okay, I am writing a program for full adder. So in the full adder, see on the right, I have shown the structure of a full adder also. So first we will write a program for full adder and then we can call the full adder 4 times. Once you call 4 times, your ripple carry adder would have been completed. So now we'll start with our program module X. So X, Y and C in, S and C out. So I have mentioned what are the inputs, what are the outputs. So for carrying our intermediate value, see here I'm having some intermediate signal and that is going to all our gates. So those are called as wires. So it is storing the intermediate signal. So what is this? Using structural level model, we can use this. So easily I know the structure, so I can go for the structural modeling. So what is this first gate? Which is Xor gate. What are the inputs X and Y? What is your output? That is, I'm mentioning it as W1. That is what I have mentioned previously as a wire. So Xor of, what is the name I am giving to this gate? G1. So which is W1 comma X comma Y. Again the second gate which is Xor G2. What is the output? Sum is the output. What are your inputs? W1 will be one of your input and one more is your carry input. And again a AND gate. What is the AND gate name? G3. What is the output of AND gate? I am giving it as a wire which is W2 and inputs is X and Y. Okay, which is G4 over here. Again G3 means you can take this as G3. So what is G3? We will be having output as X2, I mean W2 and W1 as well as your CI is the input. And what is C out? I mean C naught, which is C naught as output and W2 and W3 are your input. So this is a program for a full adder. Now I am going to write for a ripple carry adder, that is a 4-bit ripple carry adder. So the input must be 3 down to 0 x comma y. Output will also be 3 down to 0 s and output is c naught. So now we are going to instantiate 4 1-bit full adders. Okay, so now see full adder, I am calling the full adder program. So my main program is a ripple adder. In that program I am calling or using the term as, I am calling the module named as full adder. So full adder and the name of that code I am giving as it is our wish. So u1, what are the inputs? X of 0, Y of 0. See in full adder you have mentioned as X comma Y comma carry I S comma C naught. In the same way you have to mention X, X naught, Y naught and initially your input carry will be 0 and again first bit is sum naught and the data that will be going as the output of the full adder is nothing but W1. I am just using as W1. So whenever I am executing this program, when the program comes across this line, it will be searching for the program or the module named full adder and it will be passing the data. So whatever data is over here, X of 0, Y of 0, 1 bit of 0 which is S of 0 and W1 into this program and this program will be executed. Again it will be returning the data and again it will be coming back. Again it will be doing for the second full adder. In the same way x1 y1, so here now the carry will be w1, again s1 will be the sum and w2 will be the carry. Again this will be going and this program will be executed and again your output will be coming and again u3 will be executed and u4 will be executed. So final output is c naught. Again this program will be executed. So which means I am calling my main full adder 4 times and I have already written the code of a full adder by using structural modeling. This is a 4-bit triple carry adder by using full adder. And a simple program I am showing you for a data path design which is multiplier. So you all know what actually is a multiplier. So I am going to multiply my inputs A and B and I'm going to store my output as P. So the input is 7 down to 0 which means 8-bit pin, which is A and B are your input. So I'm going to store my output which is a 16-bit. We know when you are multiplying both 8 bits we'll be getting 16 bits. So 16 means 15 down to 0 which is P. I'm just assigning P is equal to A cross B. So what type of modeling is this? It is nothing but it is a data flow modeling. When I know the data, what is the data flow? When I multiply A and B, I am going to get a value that has been assigned to a variable. That variable has been declared as an output variable. So this is a simple 8-bit multiplier program. So in this module or in this video, we have seen about full adder, using ripple carry adder, using full adder, as well as half adder, using all different types of modeling, and also data flow modeling of your 8-bit multiplier. I hope you understood the video. Thank you.